So hello students, in this video we will be discussing about Poisson's ratio. Students, in the previous classes we have studied about longitudinal strain. So what is longitudinal strain that we have studied? That was, let us consider we have a wire of length L, and when we apply a deforming force on the wire, the length of the wire increases. Let us consider the length of the wire is increased by delta L. So it is the natural phenomena that due to natural phenomena, what happens whenever we increase the length of anything, the width of that thing decreases. You might have seen when you increase the length of the rubber band by applying the force, you will be able to see that the length or the width of the rubber band decreases. That is, we have not studied earlier, that we will study here. Longitudinal strain we have already studied, that is change in the length after applying the deforming force divided by the original length. And let us consider the area of cross section in which the diameter of the wire initially was d, and after applying the deforming force, let us consider that the diameter is decreased, that is changed by delta d. Here the diameter is decreasing with the increase in length. If we would have decreased the length by applying this force in this direction, the diameter would have increased. Okay? The diameter would have increased. But here we have considered that with the increase in length, the diameter is decreasing. So in case of diameter, we used to say that as a lateral strain. So lateral strain, like strain, longitudinal strain, lateral strain will be delta d, that is change in diameter upon original diameter. Here we will put negative sign because the diameter is decreasing with the increase in length. Clear? Here Poisson's ratio says that the ratio of lateral strain divided by the longitudinal strain, that is lateral strain is equals to minus delta d upon d multiplied by longitudinal strain, that is delta d divided by L. So finally we get to the conclusion. Poisson's ratio is symbolized as nu is equals to minus delta d upon delta L multiplied by capital L, that is the original length of the wire, divided by small d, that is the original diameter of the wire. Here this negative sign shows that with the increase in length, the diameter will decrease, and with the decrease in length, the diameter will increase. This is what the negative sign shows here. Here when we talk about the unit and dimension, here strain will have the strain is a unitless quantity, and here also longitudinal strain will be a unitless quantity. Therefore this Poisson's ratio is unitless as well as dimensionless as well. So here with the Poisson's ratio, in this video we will be discussing about elastic potential energy of a stretched wire. Why elastic? Elastic means when we elastic nature means when we are applying any deforming force, and when we leave it, the shape of the material goes to its initial position or the initial part, that is the elastic behavior. And potential energy, that whatever the force we are applying, due to the applied force, the material or the molecules are changing its position from here to here. So when the force is applied and the displacement is happening, the work is done, and this work done is stored in the form of energy, and that energy is known as potential energy. Since it is elastic in nature, that is why we call elastic potential energy of a stretched wire. Let us consider we have a wire of original length capital L, and the original area of cross section, let us consider it to be capital A. When we apply the deforming force, let us consider the length is increased by small l. So here we already know that from Young's modulus, it is equals to force multiplied by original length divided by area of cross section multiplied to the change in the length after applying the deforming force. So from here we can consider force is equals to YAL divided by capital L. Here when we move further, when we are talking about the work done, let us consider the work done to increase the length from L to L plus delta L. Let us consider that delta L is equals to L only. So we are increasing the length of the wire. It was initially L, and when we increased it, it became L plus small l. And small l, where it was, when small l was here, it was 0, and when small l was here, it was small l. So from 0 to L. Work done is equals to force applied multiplied by displacement. So we are integrating. We will calculate the small value of the increase in length, and accordingly we will integrate the whole part from 0 to small l, and we will get the total distance covered here, that is small l. So integrating the whole part, force multiplied by displacement from 0 to small l, YAL divided by capital L is constant. This L is integrated with respect to dl. So integration of L becomes L square upon 2 from up 0 to L. So it becomes L square 1 by 2 L square. Okay, after integration we get L square upon 2. So when we solve it further, we get upper limit minus lower limit, that is L square by 2 minus 0 upon 2. So 0 upon 2 is 0, that is why we are cancelling that part already. So we are left with 1 by 2 y into a upon L multiplied by L square. If we multiply both sides, numerator and denominator, by L, what do we get over here? That 1 by 2 YAL divided by L into L, that is L square. Change in length divided by original length is strain, and strain ka whole square. Therefore, it is equals to 1 by 2 Young's modulus multiplied by A into L. That is, area multiplied by length is called the volume. This is the volume of the wire, and multiplied by L into L, that is change in length upon original length, is equals to strain, and strain ka whole square have been put over here. So when we move again further, so we already know that modulus is equals to stress upon strain. So we can write it over here that y, that is modulus, Young's modulus multiplied by strain, is equals to stress. So Young's modulus multiplied by one of the strain becomes stress, and volume is left over here, and one strain is here. So finally we get to the conclusion that 1 by 2 multiplied by stress multiplied by strain into volume is equals to the work done in case of wire when it is stretched. And this work done is stored in the form of potential energy, that is potential energy is equals to 1 by 2 into stress multiplied by strain into volume. And when we talk about potential energy per unit volume means divided by V, we denote it by small u. When we divide it both sides by V, so V and V, that is volume, gets cancelled. So we are left with potential energy per unit volume is equals to 1 by 2 multiplied by stress multiplied by strain. So that's all with the video. Thank you very much for watching.